So unit 4 starts from it starts from kinetics, but we always do this chapter. This is easy, and we will be moving from like hard to the like easy to hard. Okay. So lattice energy. Basically, um, as we know that all ionic compounds have a lattice structure, like I can say giant ionic lattice structure. Okay. Or of course, when we are going to form an ionic compound, so we need ions like Na positive ion and Cl negative ion. Okay. In a giant lattice structure, a lot of cations and a lot of anions are present, isn't it? Like that's why we are saying that this is a giant structure due to the presence of a lot of cations and a lot of anions. So of course there would be very strong electrostatic force of attraction. That's the reason we say that ionic compounds are stronger. They are solid at room temperature. They have high melting and boiling point. So that's the reason. You know why? Because there is a very strong electrostatic force of attraction. So as we know that bond formation is exothermic. Okay. Bond formation is exothermic, so energy will be released, of course, when we will be forming an ionic compound. So the energy will be released. So we always say that this is always exothermic. Some processes are might like they sometimes they are endo, sometimes they are exo. Like enthalpy change of formation, as you know, we have discussed in unit 2. Enthalpy change of formation, it may be exo, it may be endo. But we used to say neutralization is always exothermic. Okay. In the same way, lattice energy is always exothermic. You know why? Because in this, we are going to form 1 mole of ionic lattice. I'm repeating. In this, I'm going to form 1 mole of ionic lattice. And when we are going to form 1 mole of ionic lattice like this structure, so I need to have oppositely charged ions. Like in this case, I am going to form sodium chloride, but it doesn't mean that that ionic compound is only a sodium chloride. No, it may be magnesium chloride, it may be calcium oxide, it may be magnesium oxide, it may be aluminium oxide, it may be magnesium nitride, isn't it? It may be potassium chloride. So, whatever the ionic compound is, we need to know the oppositely charged ions like cations and anions. Okay, so always exothermic. Ions are going to attract with each other and they are going to form an ionic solid. Since this is the bond formation, so that's why it's always exothermic. Okay. Um, then what is lattice structure? Like you can see, this is the lattice structure. So we can define this lattice structure as ions are arranged in a regular pattern. When the ions are arranged in a regular pattern, so this is known as a lattice structure. Okay. Or like in a lattice structure, like you will see multiple cations and anions like that. Okay. A lot of ions are present. So due to this, there would be very strong electrostatic force of attraction. So this is a very, yeah, like you can say strong structure, hard, more energy would be required to break down the lattice, like to overcome the force of attraction. So generally, this is very strong. And also, um, why do we discuss lattice energy? We have to discuss the strength of an ionic compound, which is stronger and which is weaker. Like we knew before, as like strength is going to like you can say is depending on the two factors, charge and the size. Let's say sodium chloride and magnesium chloride. So magnesium chloride is stronger. Why? Because magnesium is in group 2. Magnesium is in group 2 or sodium is in group 1. So in group 2 means that magnesium is going to have +2 charge. Okay, like that. and sodium is going to have +1 charge. Since chlorine are same, so I'm not supposed to consider chlorine. This is the same. Okay, I'm not going to look at this number. I'm going to look at the charge first. So the charges are different. So higher the charge, stronger the force of attraction. Stronger would be an ionic compound. Weaker the charge, like sodium is +1, that is weaker. Weaker the charge, lower the charge, weaker the force of attraction, weaker would be an ionic compound. It's all about the charge. And sometime you will see that sometime the charges are same. When the charges are same, then you have to look at the size. Okay, when the charges are same, then you have to go for the size. Let's say in this case, you can see in this case, you can see the charges are same, +1, +1, -1, -1. Since the charges are same, then we have to go for the size. As we know that bromine is larger than chlorine. So when the bromine is going to have a larger size, so it's just like, let's say this is bromine. This is the nucleus of bromine and this is sodium. Okay. So attraction between sodium and this bromine would be weaker. Attraction is weaker. And if you are looking at this, since the size of chlorine is smaller and this is sodium, since the size of chlorine is smaller, so its attraction would be stronger. What does it mean? That the size is inversely proportional to the strength of an ionic compound. Size is inversely proportional to the strength of ionic compound. When the size is larger, so the strength of ionic compound would be weaker. And when the size of uh, like an ion is smaller, okay, so the attraction would be stronger. So the strength of ionic compound would be stronger. Like it's inversely proportional. Size is inversely proportional to the strength. As I have mentioned, charge is directly proportional to the strength of ionic solid and size is inversely proportional to the strength of ionic solid. Okay. Whatever the compound is given, only you have to see the two factors, charge and then the size. But we have another way to represent, like to identify the strength of acid, that is called lattice energy. Lattice energy will be describing the strength of acid if the lattice energy is more negative. Like let's say sodium chloride is minus 700 kilojoules per mole. Minus means this is an exothermic, of course. So, and for magnesium chloride, the lattice energy is minus 1400. Okay. For the sodium chloride, it's minus 700. And for the magnesium chloride, it's minus 1400, right? So, this is the more negative number. If this is more negative, so the strength of ionic compound would be stronger. And if this is less negative, so the strength of ionic compound would be weaker. That's the criteria. So that's the application of the lattice energy, we can say. When the lattice energy is more negative, so the strength of ionic compound would be higher, stronger. And if the magnitude of the lattice energy is less, like the lower number, like the less negative, or I can say the less exothermic, so the strength of ionic compound would be weaker. The same thing, but the criteria is different. Of course, we are going to discuss the strength of an ionic compound on the basis of lattice energy. Okay. If this is more exothermic, so the strength of ionic compound would be stronger. And if this is less exothermic, so the strength of ionic compound would be weaker. Okay. And then, that's the normal term. Like lattice energy is the normal term. Like what do we do in this? We have to form an ionic lattice. Let's say I'm going to form sodium chloride. So I need to have Na plus ion and Cl minus ion. है ना? If we have these two ions, they will be attracting with each other. They will be forming ionic solid, that is sodium chloride, simple. So then we have standard terms. If you remember, you used to discuss standard enthalpy change of formation, standard enthalpy change of neutralization, standard enthalpy change of like standard enthalpy, standard conditions. What are the standard conditions? Temperature that is supposed to be 298 Kelvin. Then we have pressure that is 1 atm. Then we have concentration that is 1 mole per decimeter cube. Okay. So if we have these conditions, so then we will be calling this as standard enthalpy change of lattice energy. And if we have another, like if we have a temperature other than this, it may be 300 Kelvin, it may be 400 Kelvin, it may be 100 Kelvin. If we have a temperature other than this, so means that this is going to be the normal lattice energy. Okay. So we have to look at the standard terms. If we have these values, so means that this is going to be, this process is going to be at the standard conditions. So what is standard enthalpy change of lattice energy? Energy released when 1 mole of ionic solid is formed from the gaseous ions under standard condition. Like in easier words, I can say I'm going to form magnesium oxide. I'm going to form magnesium oxide. Okay. So if I'm going to form magnesium oxide, that is an ionic solid. So, the standard condition is that this is mandatory to have 1 mole of product. If you can see the definition, 1 mole of ionic solid is formed. 1 mole of ionic solid is formed. Okay. So this is mandatory. This is mandatory to have 1 mole of ionic solid. Remember, this is mandatory. And then what are the reactants? The reactants should be in gaseous state. The reactants should be in gaseous state. Okay. So let's say not only the gaseous state, but also ionic state. But also ionic state. Remember, this is very important. Remember. So I'm going to form magnesium oxide. So I need to know the two ions, Mg2 plus ion and O2 minus ion. Both ions should be in the gaseous state, not in their standard state. Of course, we know that the standard state for magnesium is solid and standard state for oxygen is O2 and gas. But this is not O2. According to the definition, I need to know gaseous ions. But yes, this is understood. You need to know what is the charge on magnesium, what is the charge on aluminium, what is the charge on potassium, lithium, barium, rubidium, aluminium, iron. Like we must know the charge. Or if I can say I'm going to form magnesium nitride solid. Okay, I'm going to form magnesium nitride solid. So I need to have Mg2 plus gas, isn't it? And I need to have N3 minus gas. As we know that the charge on nitrogen is -3 because this is in group 5 of the periodic table. And also we can predict the charge after looking at the formula. Since you can see this is 2, this is the charge for magnesium and this is 3, this is the charge for nitrogen. So Mg is +2, nitrogen is -3. So I wrote the charges, I wrote the elements, that's it. Let's say I'm going to form aluminium oxide, that is solid. So I need to write ion of aluminium, that is +3. As we know, the charge on aluminium is +3. And then O2 minus, as we know that the charge on oxygen is -2. In gaseous state, then you have to balance the equation. Again, I am saying it should be 1, 1, 1, 1. If you will be writing other than this number, so it would not be called as standard enthalpy change of lattice energy. And also, next thing is that you need to write down the ions, not in their standard states. That's another difference between the formation and the lattice energy. Okay. Or I can say, um, then what if, what if I'm going to write magnesium chloride? What if I'm going to write magnesium chloride? Of course, magnesium chloride is an ionic compound and it's a solid at room temperature. So what am I supposed to write? Mg plus 2 and 2Cl minus gas, and this is gas. Again, this is called standard enthalpy change of lattice energy. Simple. Because you know why? Because I have formed 1 mole of a product. If this is 1 mole, so that would be called standard enthalpy change of lattice energy. Sometime he will be giving you an equation and would be asking about the name of the process. Is that formation? Is that lattice energy? Is that neutralization? Is that atomization? Is that ionization energy? Is that electron affinity? So we will be discussing all of the things all together, and we must know whether the substance, whether the process is exothermic and whether the process is endothermic. We must know these things. Okay, then like this is very important. Okay, always exo or always endo. This is always exothermic because the ions are going to combine with each other. What does it mean? The bond is going to be formed. So this means that this is exothermic. Okay. Then we have, it's a used to, like it's not a new term. You must, yeah, like you knew before, standard enthalpy change of formation. What is this? Means that 1 mole of a compound is formed irrespective of the compound. What the compound is, we don't care. It may be ionic, it may be covalent, it may be anything else. It can be molecule, anything, anything. So when 1 mole of a compound is formed from its elements, not the ions. You're noticing the difference between the lattice and the formation. In the lattice, we were writing down the ions, and in the formation, we are writing down the elements. That's the first difference. Okay. And then again, the same criteria. This should be one, 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 one. For the standard state, we need to have 1 mole of ionic solid. Okay. So you can see, as I have to form sodium carbonate, and we know that this is the standard enthalpy change of formation. So what do? We need to write sodium solid in the reactant side. You know why? According to the definition, the compound is formed from its elements. Elements. The compound is from the compound is formed from its elements in their standard states. Sodium is solid. Sodium is a metal, and this is solid at room temperature. Carbon is a solid. Even it's not a metal, but it's solid at room temperature. Oxygen is a gas at room temperature. So we must know the we must know the state symbols. So overall, I can say this is the formation. Okay. Then we have to balance the chemical equation. Again, don't write any number over there. Okay. And then let's say I have to form aluminium oxide. So to form aluminium oxide, we need to write the elements in their standard states. Aluminium is solid and oxygen is a gas. It's a diatomic gas. So for the balancing equation, we are supposed to write 3 by 2. Rather than writing any number in the product side, we can also balance in this manner. Okay. But again, we must not write any number in the product side. Then you can see these equations. Again, this is the formation. Okay. So let's say this is an alcohol. It's a liquid at room temperature. It's a state sample. According to the definition, we have to write down the state samples. So in the standard state for alcohol is liquid at room temperature. Then I need to write down the reactants, that is carbon solid, hydrogen gas, and oxygen gas. To balance this, I did half, I did two, equation is balanced, and that's it. And for this one, H2O is liquid at room temperature. I'm going to write down the formation equation. So I need to write down the reactants in their standard states under standard conditions. We know that hydrogen is a diatomic gas. We know that oxygen is a diatomic gas. They will be reacting together. They will be forming water. That is liquid at room temperature. This is called enthalpy change of formation. So when the equation is given to you and you have seen that in the product side, we have 1111 and we have elements in the reactant side. So it shows that this is the formation equation. And if you can see the ions in the reactant side, okay, if you can see the ions in the reactant side, so means that this is the equation for the lattice energy. Okay, or this is very important thing. It may be exo, it may be endo. It's not fixed. It's not fixed. Sometime it may be exothermic, sometime it may be endothermic. If you remember, you used to have the values for the enthalpy changes of the reactants and the products. I'm talking about unit 2. So what we used to do, we used to apply the formula product minus reactant. After solution, sometime we used to get the positive answer, sometime we used to get the negative answer. If we got the positive one, so means that the process is endothermic. And if we got the negative one, so means that the process is exothermic. Hmm, okay. So that's why I have written it may be exothermic, it may be endothermic, depends on the values of the reactants and the products. What the examiner will give us depends. But the lattice is always exothermic. This is understood. This is understood because in a lattice, only the bond is being formed. The bond is not going to break down. Only the bond is going to form. So when the bond is being formed, so this is going to be exothermic. But in formation, in the whole equation, uh, both processes are taking place. Both processes are taking place. Bond is being broken down and bond is being formed. So of course we have to see, isn't it? Then we have to see. That's why I have written it may be exothermic and it may be endothermic. Okay, that's it. So then you can see the next process that is called atomization. Standard enthalpy change of atomization. What is this? As the name indicates, as the name indicates, when something changes from solid to gas, as the name indicates, when something changes from solid to gas and from molecule to atom. Basically, we have two things. We generally talk about metals and a non-metal. If we talk about the metals, so for the metal, it's solid to gas, and for the non-metal, it's molecule to atom. Remember, remember, for the for the metals, it's from solid to gas, and for the non-metal, it's from molecule to atom. Okay. So for both processes, we use the same term that is called atomization. Solid to gas is for metal, and molecule to atom is for the non-metal, and molecule to atom is for the non-metal. Let's see. This is non-metal. It's solid at room temperature. It's solid at room temperature. It's solid at room temperature, and it's a molecule. Since this is a non-metal, it's not a metal. So we can atomize it. So this molecule will be changing into atom. Again, we need to have 1 mole. Again, we need to have 1 mole. Again, we need to have 1 mole. Okay. So you are not supposed to write down any number. We are not supposed to write down any number in the product side. We are not supposed to write down any number in the product side. Again, the same criteria. Again, the same criteria. Okay. Again, the same criteria. For all, we need to write down 1, 1. For atomization 1, for atomization 1, 1, 1, 1. Okay. For the formation 1, 1, 1, 1. And for the lattice energy, we need to write 1, 1, 1, 1, 1. Remember, this is the mandatory thing that we need to know. For atomization, 1, 1, 1, 1. So this is standard condition. When 1 mole of an atom is formed, when 1 mole of an atom is formed from the gaseous state, when 1 mole of an atom is formed from the gaseous state. Okay. So this is one, this is one, this is one, this is one, this is one. Okay. Let's say if this is metal, this is solid at room temperature. So from solid to gas is atomization. Solid to gas, it's atomization. Solid to gas, it's atomization. Solid to gas, it's atomization. Simple. And it's molecule to atom atomization, molecule to atom atomization, molecule to atom atomization. For the non-metals, molecule to atom. For the metals, it's solid to gas. The same thing, but we can atomize the metals and we can also atomize the non-metals. So what is the nature of the process? Is this exo or endo? This is always endothermic. Always endo. You know why? Because in the solid state, the particles are attracted together in a stronger manner. And when we are going to convert this solid into the gas, so what we are doing, we are going to overcome the force of attraction. We are going to overcome the force of attraction. So we are providing energy and the solid is going to absorb energy. That's why the process is endothermic. Let's say we have a molecule. So for a molecule, atoms are attracted together. When we are going to provide energy, so we are going to overcome the force of attraction. The molecule is absorbing energy. So means that this is going to be endothermic. So I have written it's always endothermic, as the lattice energy were always exothermic, and the enthalpy change of formation may be exo, may be endo, and in the same way the atomization would be always endothermic. Okay, so the atomization would be always endothermic. Why? Yes.
Sorry, can you explain how is it endo again?
In the solid state, the particles are joined together in a stronger manner like that. Let's say this is the solid state, okay? And I'm going to provide energy and the molecules are going to, you can say, far away from each other. So what did you do? You have overcome the force of attraction. How? You have provided energy and the solid has absorbed your energy. Since the energy is being absorbed by the solid, so means this is an endothermic. It's not going to release energy. Energy is going to absorb by the solid. That's why it's endothermic. Same goes for the molecule. Let's say
Okay.
it's iodine molecule. when you are going to provide energy, so the iodine molecule is going to absorb your energy and the bond is going to break down after providing the energy. That's why the process is endothermic. And the iodine atom is formed, means you have broken down the covalent bond. How did you break down the covalent bond? You have provided some sort of energy. It may be heat energy, it may be electrical energy, but it needs an activation energy to break down the bond. So overall this is going to be endothermic. Overall this is going to be like endothermic. Okay. Um, and then we have electron affinity. Basically, electron affinity is the reverse of ionization energy. Electron affinity is the reverse of ionization energy. In ionization energy, we lose electron, like we remove electron from the outer shell. In electron affinity, electron is added. In ionization, electron is removed. In electron affinity, electron is added. It's vice versa, I can say. Okay. So like generally the people think ionization means it may be loss, it may be gain. No. Ionization is only loss of electron. Electron affinity means attraction. This term is only used for the non-metals because generally non-metals gain electron. Chlorine, bromine, oxygen, nitrogen, okay, phosphorus, sulfur. It's this term is used for the non-metals. Like let's say it's oxygen. When it would be gaining one electron, it would be forming an oxide. Nitrogen would be gaining one electron to form nitride. Phosphorus will be gaining one electron to form phosphide. So it depends upon how many electrons the elements is going to gain to convert from the normal state to the anionic state. Okay. So that's